Every star is burning. Every black hole is tearing matter apart at velocities beyond comprehension. Galaxies are colliding in slow, catastrophic ballets that span millions of years. And yet, when we step outside on a clear night and look upward, there is only silence, a silence so complete it feels almost deliberate, as though the universe has chosen to keep its violence a secret. This is the quiet that should not exist. The absence of sound where physics tells us there should be chaos. And understanding why the cosmos remains mute reveals something unexpectedly tender about the nature of space itself. If these slow reflections help carry the mind toward rest, a subscription means more quiet hours like this one, waiting whenever they might be needed. The stars are screaming, in their way, and this is the story of why we cannot hear them. The universe, as it turns out, is not silent at all, though you might be forgiven for thinking otherwise when you stand beneath the stars on a clear winter evening and hear nothing but your own breathing and perhaps the distant call of an owl settling in for the night. The truth is rather more interesting than our ears would suggest, for space is filled, absolutely saturated, with energy that travels in waves, energy that physicists call electromagnetic radiation. And this radiation permeates every region of the cosmos, from the spaces between galaxies to the gaps between the pages of the book resting on your bedside table. It is a peculiar thing to consider that you are at this very moment being bathed in radiation that has traveled from the most distant corners of the observable universe. Radiation that passed through billions of light years of nearly empty space just to arrive at your bedroom, where it continues on its journey, largely indifferent to your presence, as it has been indifferent to the presence of every planet and moon and dust cloud it encountered along the way. This understanding that the universe hums with invisible energy did not come easily to us, and like many of the most profound discoveries in science, it arrived through a combination of careful reasoning, persistent observation, and what we might politely call fortunate accidents. The story of how we came to know that space is singing, or would be if we had the proper apparatus to hear it, begins in earnest with a German physicist named Heinrich Rudolf Hertz, who in the year 1887, in a modest laboratory at the Karlsruhe Polytechnic, produced and detected the invisible waves that James Clerk Maxwell had predicted must exist some 2 decades earlier. Hertz was not thinking about the stars when he constructed his spark gap transmitter and his simple loop receiver. He was thinking about the elegant mathematics of Maxwell's equations and whether those equations described something real, something that could be made to dance across a room and ring a distant bell, so to speak. And ring it did, for when Hertz sent sparks jumping across a gap in one circuit, he observed tiny sparks appearing in the gap of another circuit clear across the room, with no wire connecting the two, no physical medium carrying the energy other than the invisible waves themselves. These were radio waves, though the name would come later, and their discovery opened a door onto a universe far stranger and more energetic than anyone standing in that laboratory could have imagined. It would be another 45 years before anyone thought to point a radio receiver at the sky. And when someone finally did, the discovery was, once again, entirely accidental. In 1932, a young radio engineer named Carl Guthrie Jansky was working at Bell Telephone Laboratories in New Jersey, tasked with identifying the sources of static that interfered with transatlantic radio communications. He had constructed a rather unusual antenna, a collection of brass pipes mounted on a rotating platform that turned slowly, completing one full rotation every 20 minutes, which earned it the affectionate nickname of Jansky's merry-go-round among his colleagues. Jansky catalogued the various types of static he received, identifying some as coming from nearby thunderstorms, others from more distant storms. But one type of static, a persistent hiss, refused to be explained by weather. It seemed to follow the sun at first, but as Jansky continued his observations through the seasons, he noticed that the hiss did not quite keep pace with the sun. It drifted slightly each day, arriving 4 minutes earlier, which is precisely the difference between a solar day and a sidereal day, the day measured against the fixed background of stars. Jansky had stumbled upon radio waves from the center of our own galaxy, the Milky Way, though he did not fully grasp the implications at the time, and Bell Telephone, having determined that the static was not something they could eliminate or charge customers to avoid, lost interest in the discovery. It would fall to others, in later decades, to build upon what Jansky had found. The most famous accidental discovery in the history of cosmic radiation came in 1965 at a facility in Homedale, New Jersey, where two radio astronomers named Arno Penzias and Robert Wilson were attempting to use a large, horn-shaped antenna for radio astronomy. The antenna had been built for satellite communication experiments and was exquisitely sensitive, which was precisely the problem, because no matter what Penzias and Wilson did, they could not eliminate a persistent, low-level hiss from their data. The hiss was the same in every direction they pointed the antenna. It was the same during the day and during the night, the same in summer and in winter, and it corresponded to a temperature of roughly 3.5 kelvins above absolute zero, which is to say, it was very cold indeed, but not quite nothing. The two scientists went through every possible explanation methodically, testing their equipment, tightening connections, accounting for interference from New York City just to the south, even climbing inside the horn of the antenna to clean out what they delicately referred to in their notes as a white dielectric material, which was, in plain language, pigeon droppings. For a pair of pigeons had taken up residence in the warm enclosure of the horn and had left evidence of their presence behind. The pigeons were captured, driven some distance away, and released. But being pigeons, they returned, and were eventually dealt with in a more permanent fashion, a detail that Penzias and Wilson did not dwell upon in their Nobel Prize acceptance speeches. Even after the pigeons and their contributions had been removed, the hiss remained, and Penzias and Wilson were forced to conclude that it was not coming from their equipment at all, that it was coming from everywhere, from the universe itself. By a stroke of good fortune, the two scientists learned of theoretical work being done at nearby Princeton University, where a group of physicists had predicted that if the universe had begun in a hot, dense state, which we now call the Big Bang, then there should be a faint glow of radiation left over from that early epoch, cooled and stretched by the expansion of space until it arrived in our era as microwaves, a cold whisper of the unimaginably hot beginnings of everything. What Penzias and Wilson had found, quite by accident while cleaning pigeon droppings from their antenna, was the cosmic microwave background, the afterglow of creation itself. Radiation that had been traveling through space for nearly 14 billion years, filling every corner of the observable universe. A relic of a time when the cosmos was so hot and dense that atoms could not yet exist. The cosmic microwave background is not loud, not by any human measure of loudness, but it is everywhere, absolutely everywhere, coming from every direction with almost perfect uniformity. A gentle bath of radiation at a temperature of 2.725 kelvins, which is just a few degrees above the coldest possible temperature, the temperature at which all thermal motion ceases. When you tune your television to a channel with no broadcast, or when you used to, in the days before digital signals replaced analog ones, a small percentage of the static you saw on the screen was caused by this radiation, by photons that had been traveling since the universe was only 380,000 years old, finally ending their journey on your television antenna, contributing a few flecks of snow to the visual noise. It is a humbling thing to consider that the static between channels was partly a message from the beginning of time, though of course the message contained no information in the usual sense, only the simple fact of its existence, only the gentle assertion that the universe was once very hot and has been cooling ever since. But the cosmic microwave background, pervasive as it is, represents only one instrument in what we might imagine as an orchestra of cosmic radiation. Every object in the universe with a temperature above absolute zero emits electromagnetic radiation, which is to say, every object that exists emits radiation, because nothing has ever been cooled to absolute zero. Nothing in all of nature has ever achieved that perfect stillness. Your own body, resting now beneath the covers, is radiating infrared light continuously, warmth leaking from your skin in wavelengths too long for your eyes to detect, but not too long for the heat-sensing pits of certain snakes, or for the thermal cameras that engineers build for various purposes. The chair in the corner of your room is radiating. The walls are radiating. The book on your nightstand is radiating. Even the ice cubes in a freezer are radiating, though feebly, each object emitting a spectrum of wavelengths determined by its temperature. The sun, our local star, is a rather more enthusiastic radiator than the objects in your bedroom, at a surface temperature of approximately 5,770 kelvins. The sun pours energy into space at a rate that defies easy comprehension, approximately 386 billion megawatts, continuously, which is to say, the sun emits in 1 second more energy than human civilization has used in its entire history. And it has been doing this for 4.5 billion years. And it will continue for another 5 billion years or so, with only modest variation. Most of this energy is emitted as visible light, which is why our eyes evolved to see the wavelengths they do. But the sun also emits radio waves, infrared radiation, ultraviolet radiation, and smaller amounts of X-rays and gamma rays, a full spectrum of electromagnetic energy streaming outward in all directions. And the sun is only one star among 200 billion stars in our galaxy. And our galaxy is only one galaxy among 2 trillion galaxies in the observable universe, each galaxy containing its own hundreds of billions of stars, each star broadcasting its energy outward across the cosmos. Beyond the stars are the remnants of dead stars. Neutron stars spinning impossibly fast. Some of them sending beams of radio waves sweeping across the sky like cosmic lighthouses. There are the accretion disks around black holes. Matter heated to millions of degrees as it spirals inward, radiating X-rays and gamma rays with furious intensity. There are clouds of gas and dust glowing with infrared light, heated by nearby stars. There are the radio galaxies, whose central engines shoot jets of particles spanning hundreds of thousands of light years, blazing with radio emission. There are quasars at the edges of the observable universe, outshining entire galaxies, powered by supermassive black holes consuming matter at rates that stagger the imagination. If we could gather up all this radiation, all the electromagnetic waves from all the sources in the cosmos, and convert it to sound at some convenient scale, the result should be, by any reasonable expectation, overwhelming. Billions of galaxies, each with billions of stars, all emitting energy simultaneously, radiation streaming through space in every direction, filling the volume of the universe with an unimaginable density of overlapping waves. The cosmic microwave background alone fills every point in space with radiation arriving from every direction. And layered upon that ancient glow are the contributions of every star and galaxy that has shone in the billions of years since. Light and radio waves and infrared radiation crisscrossing the cosmos in an unthinkably complex tapestry. It should be, by rights, a symphony so vast and so dense that no individual note could ever be distinguished. A roar of static composed of trillions upon trillions of individual sources. A wall of sound that would make conversation impossible, that would drown out every thought. And yet, when you step outside on a clear night, when you stand beneath a sky dusted with stars and feel the cool air on your skin, you hear nothing at all. The owl in the distance, perhaps, or the wind in the trees, or the sound of a car on a road far away. But from the stars themselves, from the vast cosmos wheeling overhead, there is only silence. The orchestra is playing. It has always been playing. It will continue to play long after we are gone, but we do not hear it. And the question of why we do not hear it, why the universe delivers silence instead of symphony to our waiting ears, is a question with several layers of answers, each one gentle and illuminating in its own way, each one inviting you to rest a little deeper into the quiet night. And now we come to one of the most peculiar questions ever asked in the long and patient history of astronomy. A question so simple that a child might pose it while lying in a field on a summer evening, and yet so profound that it troubled the greatest minds for centuries and ultimately revealed truths about the universe that no one had dared to imagine. The question is simply this: why is the night sky dark? Not why are some parts of it dark between the stars? Not why can we see individual points of light against a velvet background? But rather, why is there any darkness at all? Why do our eyes find rest in those vast black spaces between the constellations, when by all reasonable calculations, based on centuries of accepted cosmology, the entire sky should be blazing with light so intense that the darkness would be impossible, and the night would be as bright and as hot as the surface of the sun itself? This puzzle has come to be known as Olbers' paradox. named after a German physician and amateur astronomer named Heinrich Wilhelm Matthias Olbers, who was born in the small town of Arbergen near Bremen in 1758, and who spent his days tending to patients in the prosperous mercantile city, while devoting his nights to the quiet observation of the heavens from a modest observatory built atop his own house. Olbers was not a professional astronomer in the modern sense, for in his era, the distinction between amateur and professional was far less meaningful than it would later become. And many of the most significant contributions to astronomical knowledge came from physicians and clergymen and merchants who simply found themselves drawn to the contemplation of celestial matters in the hours when their daily obligations had concluded. He discovered several comets, including the Great Comet of 1815, and he is remembered for proposing a method for calculating cometary orbits that proved useful for many decades. But his most enduring contribution to science was the formal articulation of this troubling question about the darkness of the night sky, which he published in a paper in 1823 when he was already 65 years old. Yet, it must be said, in the gentle spirit of historical accuracy that befits our drowsy investigation, that Olbers was neither the first nor the only thinker to notice this peculiar problem with the accepted model of the cosmos. As early as 1576, an English mathematician and astronomer named Thomas Digges, who was among the first to translate and expand upon the revolutionary ideas of Copernicus for English readers, had noted in passing that if the stars extended infinitely in all directions, as he believed they did, then the sky ought to present a continuous field of light rather than the scattered points we actually observe. Digges did not dwell long upon this difficulty, and it is unclear whether he fully appreciated its implications, but the seed of the paradox was there in his writings, waiting to be cultivated by later minds. Some 4 decades later, in 1610, the great Johannes Kepler also pondered this question and suggested that the darkness of the night sky was itself evidence that the universe of stars could not be infinite, that there must be some boundary, some wall at the edge of the starry realm beyond which there was simply nothing. And thus, the darkness between the stars was simply the darkness of that ultimate void, peering back at us through the gaps in the stellar distribution. Kepler was, in a sense, offering a solution before the problem had even been properly formulated. And while his solution was not correct in its specifics, his intuition that the darkness itself contained important information about the structure of the cosmos proved to be remarkably sound. But let us now consider the logic of the paradox itself, for it is really quite elegant in its simplicity, and once grasped, it becomes difficult to shake the unsettling feeling that something about our intuitive understanding of the universe must be deeply mistaken. The argument proceeds from a few assumptions that would have seemed entirely reasonable to astronomers of the 18th and 19th centuries, and indeed to most educated people who had absorbed the prevailing cosmological views of their time. First, imagine that the universe is infinite in extent, stretching outward in all directions without limit. An endless sea of space that goes on forever, no matter how far one might travel. Second, imagine that this infinite universe is more or less uniformly populated with stars, so that while there might be local variations in density, clusters here and voids there, On the whole, the distribution of stars averages out to some roughly constant number per unit volume of space. Third, imagine that the universe is static and eternal, neither expanding nor contracting, neither beginning nor ending, simply existing as it has always existed and as it always will exist, with the stars burning steadily in their places across the measureless reaches of cosmic time. Given these assumptions, which would have seemed perfectly sensible to most astronomers before the 20th century, a troubling conclusion follows with mathematical certainty. If you look out into space in any direction, your line of sight must eventually encounter the surface of a star. It might be a star that is very close, relatively speaking, or it might be a star that is unimaginably distant, so far away that its light has traveled for millions or billions of years to reach your eye. But somewhere along every possible line of sight, there must be a star, for, in an infinite universe uniformly filled with stars, there is no direction you can look that does not eventually terminate at stellar material. To put this more concretely, imagine the universe divided into a series of thin concentric shells centered on the Earth, like the layers of an onion extending outward to infinity. Each shell contains a certain number of stars, and because the volume of a shell increases with the square of its radius, the more distant shells contain proportionally more stars than the nearer shells. However, the brightness of each individual star decreases with the square of its distance from us. Following the familiar inverse square law that governs the propagation of light through space, these two effects, the increasing number of stars and the decreasing brightness of each star, exactly cancel one another, so that each shell contributes the same total amount of light to our sky, regardless of how near or far it is. And since there are infinitely many shells extending outward forever, each contributing the same amount of light, the total light arriving at Earth from all the stars in the universe should be infinite. Or, at the very least, it should be equivalent to the situation where every point in the sky is occupied by a stellar surface, so that we would find ourselves enclosed within a sphere of blazing light as hot and as bright as the photosphere of an average star. The surface of our own Sun has a temperature of approximately 5,500 degrees Celsius, and this is the temperature that the entire sky should reach if the universe were truly infinite, eternal, static, and uniformly filled with stars. The night would be as bright as day, and the day would be no darker than the night, and the whole of space would glow with a relentless brilliance that would make life as we know it utterly impossible. This is not merely a matter of uncomfortable warmth or inconvenient illumination, for at such temperatures all water would vaporize. All organic molecules would be torn apart, and the Earth itself would be nothing but a cinder drifting through an ocean of fire. And yet, here we sit, in comfortable darkness, watching the gentle stars prick through the velvet black of a cool and quiet night. And the profound disagreement between theoretical prediction and observed reality tells us that at least one of our assumptions must be wrong. Olbers himself proposed what seemed like a reasonable solution to this puzzle, suggesting that perhaps the light from very distant stars was absorbed by intervening material, clouds of dust and gas drifting through interstellar space that would block and absorb the light before it could reach our eyes. This seems sensible enough, for we know that dust can obscure light, and it would explain why we do not receive the full infinite blaze of stellar radiation that the mathematics predicts. But this solution, however appealing it might have seemed at first glance, cannot actually work, and the reason is thermodynamics. If interstellar dust were truly absorbing all that starlight, the dust itself would heat up as it absorbed energy, and eventually it would reach an equilibrium temperature at which it was radiating away as much energy as it was absorbing. In other words, the dust would begin to glow, becoming itself a source of light and heat, and the sky would still be ablaze, just with glowing dust instead of visible stars. You cannot hide energy by absorbing it, for the energy must go somewhere, and eventually it will make itself known as radiation. Olbers' proposed solution, while clever, was ultimately no solution at all. It is rather remarkable to note that one of the most prescient insights into the resolution of this paradox came not from a professional astronomer or physicist, but from the American poet and writer Edgar Allan Poe, who in 1848 published a curious prose poem and cosmological essay titled Eureka, in which he attempted to describe the origin and structure of the universe through a combination of intuition, speculation, and what we might generously call philosophical reasoning. Poe suggested, among many other ideas in that strange and sprawling work, that the darkness of the night sky might be explained if the universe were not infinitely old, but rather had a finite age, so that light from the most distant stars had simply not yet had time to reach us. The visible universe, in Poe's conception, was like a sphere of illumination growing outward from some primordial origin, and beyond the edge of that sphere lay stars whose light was still traveling through space, still on its way, still centuries or millennia or millions of years from arriving at our waiting eyes. This was a remarkable insight for someone with no formal scientific training, and while Poe embedded it within a great deal of mystical and somewhat confused speculation, the core idea was sound and would eventually be confirmed by the developments of 20th century cosmology. The universe is not infinitely old, and the light from sufficiently distant objects has not had time to reach us. Some decades after Poe's largely ignored essay, the eminent physicist William Thomson, better known as Lord Kelvin, returned to the paradox in a paper published in 1901, bringing to bear the rigorous mathematical tools of thermodynamics and attempting to quantify exactly how bright the sky would be under various assumptions about the distribution and luminosity of stars. Kelvin's calculations confirmed the essential logic of the paradox and helped to establish it firmly within the scientific literature, even if a complete solution remained elusive. Kelvin himself still worked within a framework that did not include the expanding universe or the finite age of the cosmos as we now understand them. And so he too found himself unable to fully resolve the puzzle, though his work helped to sharpen the question and make clear just how serious a problem it posed for the prevailing cosmological views. The darkness of the night sky, this most ancient and childlike of questions, turns out to be not merely a curiosity, but a genuine clue. A piece of evidence pointing toward profound truths about the nature of reality that lay beyond the imagination of most 19th century thinkers. The sky is dark because the universe is not infinite in age, because it had a beginning, because the light from the most distant regions has not yet had time to reach us. The sky is dark because the universe is expanding, and the light from receding galaxies is stretched and dimmed by their motion away from us, shifted toward longer and less energetic wavelengths until it fades beyond the limits of human perception. The sky is dark because the universe is not static and eternal, but dynamic and evolving, and the darkness itself is a message, a cosmic telegram written in the language of absence, telling us that the story of existence is not an endless monotony, but a narrative with a beginning and perhaps an ending, with chapters we have not yet read and pages still being written. This simple question, why is the sky dark at night, leads us gently by the hand toward the most extraordinary discoveries of modern cosmology. And it reminds us that sometimes the most profound mysteries are hiding in the most ordinary observations, waiting patiently for someone to ask the right question. Let us travel now to a mountaintop in California, to a place called Mount Wilson, where the air is thin and clear and the city lights of Los Angeles had not yet grown bright enough to wash away the stars. The year is 1929, and a man named Edwin Hubble is spending his nights in a small dome, his eye pressed to the eyepiece of what was then the largest telescope ever built. The Hooker telescope, they called it, named for the businessman who funded its construction. And its mirror measured 100 inches across, a great disk of glass that gathered light the way a bucket gathers rain. Hubble would sit in the cold for hours, guiding the telescope by hand, photographing tiny smudges of light that most astronomers of his day still believed were clouds of gas within our own galaxy. He was patient, methodical, and perhaps a little vain, but his vanity was matched by genuine skill, and what he discovered on that mountain would change everything we thought we knew about the size and nature of the universe. But before we speak of Hubble's discovery, we must first visit another observatory, in another place where the groundwork was quietly being laid. In Flagstaff, Arizona, nestled among ponderosa pines at an elevation of 7,000 feet, there stands the Lowell Observatory, founded by a wealthy Bostonian who believed he could see canals on Mars. It was here, beginning around 1912 and continuing through 1917, that a careful and somewhat overlooked astronomer named Vesto Slipher began measuring something peculiar about the light from distant nebulae. Slipher was not a flamboyant man, and his work did not attract the headlines that Hubble's later would. But he possessed a spectrograph of unusual quality and the patience to use it well. Night after night, he split the light from these faint spiral shapes into its component colors, and what he found was unexpected. Nearly all of them showed their light shifted toward the red end of the spectrum, as if something had stretched the wavelengths longer, like pulling on a spring until its coils spread apart. This stretching of light is called redshift, and to understand it properly, we must think for a moment about what light actually is. Light travels as a wave, much like ripples spreading across the surface of a pond, and the distance between each ripple, which we call the wavelength, determines what color our eyes perceive. Short wavelengths appear blue or violet, while longer wavelengths appear red or orange, and wavelengths longer still pass beyond the range of human vision entirely, becoming infrared radiation, then microwaves, then radio waves that slip through our bodies without our ever knowing they were there. When a source of light moves away from us, or when the space between us and that source is itself expanding. The wavelengths of light become stretched during their journey, pulled longer and longer like taffy in the hands of a candy maker who works with infinite slowness. The light that began its journey as blue may arrive as green, or yellow, or red, depending on how much stretching has occurred. And if the stretching is great enough, the light may redden past the point where we can see it at all. Slipher measured redshifts in dozens of spiral nebulae, and, though he did not fully understand what his measurements meant, he recognized their importance and published his findings for others to interpret. The data sat in astronomical journals, waiting patiently, the way good data often does, until someone came along with the additional pieces needed to complete the puzzle. That someone was Edwin Hubble, though we should also mention, with the gentleness that historical fairness requires, that another someone had already begun to assemble the pieces in a different way. Georges Lemaitre was a Belgian priest who was also a physicist, a combination that might seem unusual today, but was less so in the early 20th century, when the boundaries between disciplines were softer and more permeable. Lemaitre had studied at Cambridge and at the Massachusetts Institute of Technology, and he had a gift for mathematics that he applied to the equations of general relativity, those beautiful and bewildering formulas that Albert Einstein had published in 1915. In 1927, 2 years before Hubble's famous paper, Lemaitre published an article in an obscure Belgian journal proposing that the universe was expanding, that the distances between galaxies were growing with time, and that this expansion could be measured by observing the relationship between a galaxy's distance and its redshift. He had, in essence, discovered what we now call Hubble's law, but his paper was written in French and published in a journal few astronomers read, and so the discovery passed largely unnoticed by the wider scientific world. Hubble, working at Mount Wilson with his 100-inch telescope, was measuring distances. This was the crucial piece that Slipher's work had lacked. Slipher could tell you how fast a nebula seemed to be receding, based on its redshift, but he could not tell you how far away it was. Hubble could, and his method involved a particular type of star called a Cepheid variable. These stars pulsate in brightness with a rhythm as regular as a heartbeat, growing brighter and dimmer over periods of days or weeks. And the remarkable thing about them, discovered by Henrietta Leavitt at Harvard some years earlier, is that their pulsation period is directly related to their true luminosity. A Cepheid that pulses slowly is genuinely brighter than one that pulses quickly, and if you know how bright a star truly is, and you can measure how bright it appears from Earth, you can calculate how far away it must be, using the same principle that tells you a candle across a field must be farther than a candle across a room. Hubble found Cepheid variables in some of the spiral nebulae, and when he calculated their distances, he discovered they were enormously far away, millions of light-years distant, far beyond the boundaries of our own Milky Way. These were not clouds of gas at all, but entire galaxies, vast collections of hundreds of billions of stars, each one as complex as our own cosmic neighborhood. And when he combined his distance measurements with Slipher's redshift data, a pattern emerged that was simple and profound. The farther away a galaxy was, the faster it appeared to be receding, not just moving away, but moving away at a speed proportional to its distance. as if the universe itself were stretching like the surface of a balloon being slowly inflated. This is what we mean when we say the universe is expanding. It is not that galaxies are flying apart through space like shrapnel from an explosion, though that image is tempting and not entirely wrong. Rather, it is space itself that is growing, the fabric of the cosmos stretching in every direction, carrying the galaxies along with it like raisins in a loaf of bread that swells as it bakes. Wherever you are in the universe, you would see the same pattern: distant galaxies moving away from you in all directions, their recession speeds increasing with distance. Not because you occupy some special central point, but because everywhere is expanding away from everywhere else. There is no center to this expansion, no edge in the ordinary sense, just the quiet and continuous growth of the space between things. And here, at last, we begin to see how this expansion helps to resolve the paradox we have been considering. The puzzle of why the night sky is dark when it ought, by certain reckonings, to be blazing with the accumulated light of infinite stars. Part of the answer, as we have discussed in earlier passages, lies in the finite age of the universe, but the expansion adds another layer to our understanding, a cosmological dimming that shifts much of the universe's light beyond the reach of human eyes. Consider a star in a very distant galaxy, so far away that the light now reaching us began its journey billions of years ago. During all those billions of years of travel, the space through which that light has been passing has been expanding, stretching the wavelengths of the light little by little, reddening it gradually as one might redden a photograph by slowly turning up the warmth of the developing chemicals. Light that began its journey as visible blue or white may arrive as infrared radiation, invisible to us, felt as warmth but not seen as light. Light from even more distant sources may be stretched into microwaves or radio waves, forms of electromagnetic radiation that pass through our atmosphere and through our bodies without stimulating the cells at the back of our eyes. The universe is full of this shifted light, this ancient radiation that has been traveling for so long that space has stretched it past the point of visibility. The most famous example of this shifted radiation is what we call the cosmic microwave background, a faint glow that fills all of space, the remnant light of a time when the universe was young and hot and dense, before atoms had formed, when everything was a brilliant fog of light and matter intermingled. That light has been traveling for nearly 14 billion years, and in that time, the expansion of the universe has stretched its wavelengths by a factor of more than 1,000, reddening it from the brilliant glow of a cooling fire to the faint whisper of microwaves that we can detect only with specialized instruments. This ancient light is everywhere, arriving from every direction at once, but we cannot see it, and so the sky appears dark even though it is filled with the scattered remnants of creation. There is also a boundary to what we can observe, a cosmic horizon beyond which nothing can reach us, not because there is nothing there, but because there has not been enough time. The universe is approximately 13.8 billion years old, which means that light can have traveled, at most, 13.8 billion years to reach us. And you might think this would limit our view to a sphere 13.8 billion light-years in radius. But the expansion of space complicates this calculation in a way that is both counterintuitive and rather lovely. The most distant light we can see began its journey from a region of space that was much closer to us when the light was emitted. And in the time that light has been traveling, the space between us and its source has continued to expand, so that the source itself is now much farther away than you might expect. The result is that the observable universe has a radius of approximately 46.5 billion light-years, a sphere centered on the Earth, not because the Earth is special, but because our observations are necessarily centered on wherever we happen to be. Beyond this cosmic horizon lies more universe, presumably much like the universe we can see, filled with galaxies and stars and planets, and perhaps with other beings who look out at their own night sky and wonder why it is dark. But we cannot see them, and they cannot see us, because the light has not had time to make the crossing. The universe may well be infinite in extent, stretching on forever in all directions, but our view of it is limited by the finite speed of light and the finite age of everything. This is not a wall, not a barrier you could travel to and touch, but a horizon in the truest sense, a limit defined by our position and by the nature of light and time. And so the expansion of the universe accomplishes two things that help explain the darkness of the night sky. First, it stretches the light from distant stars, redshifting it out of the visible range and into the infrared and microwave portions of the spectrum, where it becomes invisible to human eyes. Second, it establishes a horizon, a boundary to the observable universe, beyond which no light has yet had time to reach us, and perhaps never will, because the expansion of space is carrying those distant regions away from us faster than their light can approach. The universe is running away from itself, carrying its most distant parts beyond our reach forever. And in this silent recession lies part of the reason we can look up at night and see darkness between the stars. In the spring of 1965, two radio astronomers working at Bell Telephone Laboratories in Holmdel, New Jersey, found themselves confronting a problem that simply would not go away, no matter how carefully they cleaned their equipment or how thoroughly they checked their calculations. And this stubborn annoyance, this persistent hiss in their antenna, would turn out to be the most ancient sound human beings had ever detected, though of course they did not know this at the time, and were rather focused on the more immediate concern of pigeon droppings accumulating inside their horn-shaped receiver. Arno Penzias and Robert Wilson had been tasked with calibrating a large antenna originally built for satellite communications, and they intended to use it for radio astronomy, which required them to account for every possible source of interference, every stray signal that might contaminate their measurements. And yet, no matter what direction they pointed their instrument, no matter what time of day or season of the year, there remained a faint but unmistakable warmth in the data, a background noise corresponding to a temperature of approximately 3.5 degrees above absolute zero, which is to say 3.5 Kelvin, and this noise appeared to come from everywhere and nowhere simultaneously, filling the sky with perfect uniformity in a way that seemed quite impossible if it originated from any particular source. They cleaned the antenna thoroughly, removing what they delicately referred to as a white dielectric material left behind by the pigeons that had taken up residence in the horn. And still the signal persisted, and they checked their instruments again and again, and still the signal persisted. and they considered atmospheric interference and ground radiation and equipment malfunction. And still, quietly and stubbornly, the signal remained exactly where it was, unchanging and unexplained. A gentle hiss from everywhere at once. Meanwhile, just 30 miles away at Princeton University, a physicist named Robert Dicke and his colleague Jim Peebles were at that very moment constructing a detector specifically designed to search for precisely this kind of signal. Because they had reasoned that if the universe had indeed begun in a hot, dense state, as certain cosmological theories suggested, then the afterglow of that primordial heat should still be detectable today, stretched and cooled by the expansion of space, but nonetheless present, a faint thermal echo of creation itself, and they were building their instrument with considerable care and anticipation, not knowing that the signal they sought was already being measured by two rather puzzled astronomers just a short drive down the road. The connection between these two groups came about through a series of conversations and telephone calls. And when Penzias and Wilson learned what the Princeton team was looking for, and when Dicke and Peebles learned what the Bell Labs team had found, the significance of that stubborn 3.5 Kelvin hiss became suddenly and beautifully clear. And what had been an engineering nuisance revealed itself to be something far more profound, namely the oldest light in the universe, the cooled remnant of the moment when the cosmos first became transparent, the echo of an epoch so distant that the stars themselves had not yet begun to form. But this discovery, momentous as it was, did not emerge from nowhere. And the history of science is often a history of overlooked predictions and forgotten papers. And so we must travel back 17 years to 1948, when two young physicists named Ralph Alpher and Robert Herman published a remarkable calculation that would be largely ignored for nearly 2 decades, gathering dust in the scientific literature, while the universe it described continued its patient expansion, indifferent to whether anyone was paying attention. Alpher and Herman had been working on the problem of how the lightest elements, hydrogen and helium and traces of lithium, had formed in the early universe, and their calculations led them to an interesting prediction, namely that if the universe had indeed begun in a hot, dense state, then the radiation present in that early fireball should still exist today, stretched by cosmic expansion to much longer wavelengths and cooled to a temperature of roughly 5 degrees Kelvin, give or take a few degrees depending on the precise assumptions one made. And they published this prediction in a serious scientific journal, and then they waited for someone to go out and measure it. And they waited, and the years passed, and almost no one seemed particularly interested in looking. There were various reasons for this neglect, some technical and some sociological, and the observational techniques of the late 1940s and 50s were perhaps not quite up to the task, and the theoretical framework connecting cosmology to observable phenomena was still being developed. And some physicists simply did not take the hot Big Bang model seriously enough to invest their careers in testing it. And so, the prediction of Alpher and Herman sat quietly in the scientific literature, correct and important and almost entirely ignored, while the microwave background radiation they had described continued to fill every cubic centimeter of space with its gentle warmth, patiently waiting to be noticed. When Penzias and Wilson made their discovery in 1965, Alpher and Herman were still alive and still active in science, and one might imagine they felt some mixture of vindication and perhaps a certain wistfulness at having been proven right so many years after the fact. And the Nobel Prize for the discovery would eventually go to Penzias and Wilson in 1978, which was certainly appropriate given that they had made the actual measurement, though Alpha, in particular, spent some of his later years expressing a certain understandable frustration at the way history had unfolded. And this, too, is part of the story. The human element of scientific discovery with all its complications and imperfect fairness. But let us now turn to what this cosmic microwave background actually is. And to understand it properly, we must travel back to an epoch so ancient that the word ancient hardly seems adequate. A time when the universe was approximately 380,000 years old, which sounds like a very long time by human standards, but was in fact the cosmic equivalent of infancy, a fleeting moment after the beginning of everything. And in this early universe, conditions were extraordinarily different from anything we experience today. In the first few 100,000 years after the Big Bang, the universe was filled with a hot, dense plasma, a seething mixture of protons and electrons and photons, and the photons could not travel very far before colliding with a free electron and scattering off in some random direction. And so, light could not propagate freely. And the universe was opaque in much the same way that the interior of a star is opaque today, with light bouncing endlessly from particle to particle, unable to escape or to travel in a straight line for any appreciable distance. And if you had somehow been present in this era, which of course you could not have been for a great many reasons, you would have seen nothing at all, because light itself was trapped in an endless maze of collisions. But the universe was expanding and cooling all the while, and as the temperature dropped, a remarkable transition became possible, because at a certain threshold, roughly 3,000 degrees Kelvin, the electrons slowed down enough to be captured by protons, forming neutral hydrogen atoms for the first time. And this process is called recombination, which is a slightly misleading name since the electrons and protons had never been combined before and were not technically recombining. But scientific terminology is not always perfectly logical, and the name has stuck despite its minor inaccuracy. When recombination occurred, the universe underwent a transformation as profound as any in its history, because with the free electrons now bound up in atoms, there was suddenly nothing for the photons to scatter off of, and space became transparent almost instantly on cosmic timescales, and the light that had been trapped for hundreds of thousands of years was suddenly free to travel in straight lines across the universe. And it has been traveling ever since, for 13.8 billion years now, growing cooler and more stretched with each passing epoch. And this light, this afterglow of the moment when the universe first became see-through, is what Penzias and Wilson detected with their pigeon-infested antenna in New Jersey. The light that was released at recombination was originally in the visible and near-infrared range, glowing with a temperature of about 3,000 degrees, roughly the color of a somewhat cool red star. But the expansion of the universe has stretched those wavelengths by a factor of roughly 1,000, shifting them from visible light down into the microwave portion of the electromagnetic spectrum, and cooling them from 3,000 degrees to just 2.7 degrees above absolute zero. And this is why we call it the cosmic microwave background, because it now registers as microwaves rather than visible light. though it is fundamentally the same radiation that a hypothetical observer would have seen, glowing all around them 380,000 years after the Big Bang. For several decades after its discovery, the cosmic microwave background was studied primarily from the ground and from balloon-borne instruments, and these observations confirmed that it was remarkably uniform across the sky. The same temperature in every direction to extraordinary precision, which was both reassuring and somewhat puzzling. Because if the early universe had been perfectly uniform, then there would have been no seeds for galaxies and stars and planets to form. No slight concentrations of matter that could grow through gravitational attraction into the structures we observe today. And so, cosmologists suspected that there must be tiny fluctuations in the background. Minute variations in temperature corresponding to slightly denser and slightly less dense regions in the early plasma. But these fluctuations would be so small that detecting them would require instruments of exceptional sensitivity and stability. In 1989, NASA launched the Cosmic Background Explorer satellite, known as KIOB, which carried instruments specifically designed to make precise measurements of the cosmic microwave background from above the distorting influence of Earth's atmosphere. And in 1992, the KIOB team announced results that would transform our understanding of cosmic origins, because they had detected the long-sought fluctuations, tiny variations in the temperature of the background radiation amounting to just a few 100,000ths of a degree. And the principal investigator, George Smoot, described these measurements in rather poetic terms, calling them like seeing the face of God. And while scientists are not usually given to such language, the sentiment was understandable given the significance of what they had found. These minute temperature differences, barely detectable even with the most sensitive instruments ever built, were the imprint of the primordial density fluctuations that would eventually grow into galaxies and clusters and the great cosmic web of structure we observe today. And in a very real sense, the KIOB satellite had taken a photograph of the seeds of everything. The quantum fluctuations from the earliest moments of cosmic history, frozen into the radiation field and preserved for 13.8 billion years, waiting patiently to be measured by curious primates on a small, rocky planet orbiting an unremarkable yellow star. After KIOB came the Wilkinson Microwave Anisotropy Probe, or WMAP, which operated from 2001 to 2010, and which produced maps of the microwave background with much finer resolution and greater sensitivity than KIOB had achieved, allowing cosmologists to extract precise values for fundamental cosmic parameters, the age of the universe and its geometry, and the proportions of ordinary matter and dark energy, all encoded in the subtle patterns of hot and cold spots scattered across the microwave sky. And these measurements agreed remarkably well with theoretical predictions, giving cosmologists considerable confidence that they understood the broad outlines of cosmic history, even if many details remained mysterious. And then came the Planck satellite, launched by the European Space Agency in 2009 and operating until 2013, which measured the cosmic microwave background with exquisite precision, mapping temperature variations across the entire sky down to fluctuations of just 100,000th of a degree, and producing images of the infant universe in unprecedented detail. And the data from Planck have been analyzed and reanalyzed. yielding ever more precise constraints on cosmological models. And what these measurements reveal is a universe that began in an almost perfectly uniform state, with tiny fluctuations of about 1 part in 100,000. Fluctuations that were exactly the right size to grow over billions of years into the galaxies and clusters and voids we observe today. This whisper of microwave radiation that fills all of space, this faint hiss that Penzias and Wilson mistook at first for equipment noise, is all that remains of the universe's first light. The afterglow of creation stretched and cooled beyond recognition, transformed from the blazing plasma of the early cosmos into a gentle microwave hum just a few degrees above absolute zero. And it surrounds us always, passing through our bodies and through the walls of our homes and through the rocks and the oceans and the atmosphere, unnoticed and unheard except by our most sensitive instruments. The fading echo of everything that ever was, the last whisper of the moment when the universe first became transparent, drifting quietly through space and time forever, growing fainter with each passing age, but never quite falling silent. The observable universe, that portion of space from which light has had sufficient time to reach us since the very beginning of everything, contains within its boundaries a number of galaxies so vast that the human mind struggles to hold the figure in any meaningful way. Current estimates suggest there are somewhere between 200 billion and 2 trillion galaxies scattered throughout this observable volume. And each of those galaxies contains, on average, between 100 billion and 400 billion stars. If you were to attempt counting these stars at a rate of 1 per second, never pausing to sleep or eat or rest, you would require many millions of years simply to count the stars within our own galaxy, the Milky Way, which is itself just one spiral of light among those countless trillions. The numbers involved are so far beyond ordinary human experience that they begin to feel abstract, like mathematical curiosities rather than actual things burning with nuclear fire across the darkness. And yet here we are, on our small rocky world, orbiting an unremarkable yellow star in the outer reaches of a fairly typical spiral galaxy. And the night sky appears to us as a scattering of a few thousand points of light against a velvet black backdrop. The silence of space presses against our planet like something physical, like a great quietness that has always been there and will continue long after everything we know has changed into something else. This apparent emptiness, this cosmic stillness, exists despite the fact that the universe is conducting an enormous and continuous symphony of activity, signals traveling in every direction at every moment, information streaming past us and through us in quantities that would overwhelm any attempt at comprehension. Consider for a moment the neutrino, that most ghostly of subatomic particles, so reluctant to interact with ordinary matter that it passes through nearly everything as though nothing were there at all. Neutrinos are produced in tremendous numbers by nuclear reactions, particularly those occurring in the cores of stars where hydrogen atoms are being crushed together to form helium, releasing energy in the process. Our own Sun produces neutrinos in such abundance that approximately 65 billion of them pass through every square centimeter of your body that faces the Sun, every single second of every single day. At night, when the Sun is on the other side of the Earth, those same neutrinos are still reaching you, having passed through the entire planet as though it were made of nothing more substantial than a thin morning mist. The reason neutrinos can accomplish this remarkable feat of penetration is that they interact with other particles only through the weak nuclear force and gravity, both of which are, at the scales involved, extraordinarily feeble. A neutrino produced in the core of the Sun will, on average, travel through several light-years of solid lead before having a reasonable chance of interacting with a single atom. This makes detecting them an exercise in patience and scale, requiring detectors of enormous size operated over long periods of time, waiting for the rare occasions when a neutrino does choose to make its presence known. In Japan, beneath a mountain called Ikanoyama, there exists a remarkable scientific instrument called Super Kamiokande, and its design reflects the challenging nature of neutrino detection with elegant simplicity. The detector consists of a cylindrical stainless steel tank filled with 50,000 metric tons of ultra-pure water, so thoroughly cleansed of impurities that it is among the purest substances ever created by human hands. The walls of this underground cathedral are lined with approximately 11,000 photomultiplier tubes, each one a sensitive eye capable of detecting individual photons of light. When a neutrino, on rare occasion, collides with a water molecule and produces a charged particle moving faster than light can travel through water, a faint cone of blue light called Cherenkov radiation is emitted, and the photomultiplier tubes capture this brief flash, recording the direction and energy of the event. Despite the enormous size of the detector and the constant rain of neutrinos passing through it, Super Kamiokande detects only a handful of neutrino interactions each day. Most of these come from the Sun, that reliable furnace burning just 8 light minutes away, but some arrive from more distant sources, and some are produced when cosmic rays strike the Earth's atmosphere high above. The detector operates continuously, year after year, accumulating data with the patience that neutrino astronomy requires, waiting for signals that may come frequently or rarely, depending on what the universe chooses to send our way. On the 23rd of February in the year 1987, astronomers in the Southern Hemisphere noticed that a star in the Large Magellanic Cloud, a small satellite galaxy orbiting our own Milky Way at a distance of approximately 160,000 light-years, had suddenly become visible to the naked eye where no bright star had been before. This was supernova 1987A, the closest supernova observed since the invention of the telescope, and it provided an unprecedented opportunity to study the death of a massive star in detail across the entire electromagnetic spectrum. But before the light of the supernova reached Earth, before the optical telescopes could capture images of the expanding debris cloud, something else arrived first. In the hours before the visible explosion was noticed, 3 neutrino detectors around the world recorded a brief and extraordinary pulse of activity. Kamiokande 2 in Japan, which was the predecessor to Super Kamiokande, detected 12 neutrino events. The Irvine, Michigan Brookhaven detector in Ohio recorded 8 events. The Baksan Neutrino Observatory in the Soviet Union captured an additional 5 events. In total, 25 neutrinos were captured from a cataclysmic stellar explosion occurring 160,000 light-years away, and they arrived in a burst lasting approximately 13 seconds. This was the first confirmed detection of neutrinos from a source outside our solar system, the birth of extrasolar neutrino astronomy, accomplished through the capture of just 25 particles from a supernova that likely released approximately 10 to the 58th power neutrinos in those few terrible seconds of stellar collapse. The numbers involved help illustrate why the universe seems so silent despite its constant activity. A supernova is among the most violent and energetic events that can occur in the cosmos, outshining entire galaxies for brief periods, releasing more energy in seconds than our Sun will produce over its entire 10 billion year lifetime. And yet, from such an event occurring at what astronomers consider to be practically next door, we managed to capture only 25 neutrinos. The overwhelming majority of those countless particles passed through the Earth and its detectors and continued onward into space, never interacting with anything, carrying their information away into the darkness forever. Another language in which the universe speaks, one even more recently translated by human instruments, is that of gravitational waves. In the year 1916, Albert Einstein, working on his general theory of relativity, predicted that massive objects undergoing acceleration would produce ripples in the fabric of spacetime itself, disturbances that would propagate outward at the speed of light, like waves spreading across the surface of a pond. These gravitational waves would cause space to stretch and compress in alternating directions as they passed, though the effect would be extraordinarily subtle, far too small to detect with any technology available at the time or for many decades afterward. The challenge of detecting gravitational waves lies in their extreme weakness by the time they reach Earth from distant cosmic sources. Even the most violent events imaginable, such as the collision of two black holes, each containing many times the mass of our Sun, produce ripples that, after traveling billions of light years, cause changes in distance smaller than can be easily comprehended. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, was designed to measure these infinitesimal stretches and compressions of space, and its sensitivity represents one of the most remarkable achievements in the history of scientific instrumentation. LIGO consists of two nearly identical detectors, one located in Livingston, Louisiana, and the other in Hanford, Washington, separated by approximately 3,000 kilometers. Each detector is shaped like a giant letter L, with two arms extending 4 kilometers in perpendicular directions. Laser beams travel down these arms, bounce off mirrors at the far ends, and return to interfere with each other at the junction. When a gravitational wave passes through the detector, it stretches one arm while compressing the other, causing a shift in the interference pattern that can be measured with extraordinary precision. The sensitivity required is almost beyond belief, as the detectors must be capable of measuring changes in the length of the 4-kilometer arms that are smaller than 1/10,000th the width of a proton. In September of 2015, almost exactly 100 years after Einstein's prediction, the two LIGO detectors simultaneously recorded a signal that matched theoretical predictions for the gravitational waves produced when two black holes, one 36 times the mass of the Sun and the other 29 times as massive, spiraled together and merged into a single larger black hole approximately 1.3 billion light-years away. The announcement came in February of 2016, after months of careful analysis to verify that the signal was genuine, and it marked the opening of an entirely new window through which to observe the universe. Gravitational wave astronomy had been born, adding another sense to humanity's limited perception of cosmic events. Since that first detection, LIGO and its partner observatories have recorded dozens of additional gravitational wave events, including the merger of neutron stars that was simultaneously observed across the electromagnetic spectrum, providing rich information about the physics of these extreme collisions. And yet here too we find the same pattern of vast signals and minimal detection. Gravitational waves are passing through the Earth continuously, produced by orbiting binary stars and colliding compact objects throughout the universe. But only the most powerful events occurring at favorable distances produce signals strong enough for our current instruments to detect above the constant background noise. In the western reaches of Argentina, spread across the high plains of the Mendoza province, lies another monument to the cosmic messages that pass through us mostly unnoticed. The Pierre Auger Observatory covers an area of approximately 3,000 square kilometers, roughly the size of a small country, and its purpose is to detect the highest energy cosmic rays that strike the Earth's atmosphere. Cosmic rays are not rays at all in the ordinary sense, but rather individual subatomic particles, mostly protons and atomic nuclei, that have been accelerated to extraordinary energies by processes that remain only partially understood. When one of these ultra-high energy cosmic rays enters the atmosphere, it collides with an air molecule high above the ground and produces a cascade of secondary particles, which in turn produce more particles, creating a shower that spreads out as it descends, eventually covering many square kilometers at ground level. The Pierre Auger Observatory detects these air showers using a combination of ground-based water Cherenkov detectors and optical telescopes that observe the faint fluorescence produced as the shower particles excite nitrogen molecules in the atmosphere. By measuring the timing and intensity of the signals across its vast array of detectors, the observatory can reconstruct the energy and arrival direction of the original cosmic ray. The energies involved are almost incomprehensible when considered at the scale of individual particles. Some cosmic rays arrive with energies equivalent to that of a baseball traveling at 90 kilometers per hour, all concentrated in a single proton. These particles have traveled across intergalactic distances, perhaps from the jets of active galactic nuclei or the expanding shells of supernovae, carrying with them information about some of the most energetic processes in the universe. And yet, they arrive sparsely. The highest energy events occurring at a rate of only about 1 per square kilometer per century, requiring enormous detector arrays and patient observation to accumulate enough data for meaningful study. So we find ourselves in a curious position, surrounded by messages we cannot read, immersed in signals we cannot feel, at the center of a cosmic broadcast that passes through us as though we were not present at all. Neutrinos stream through our bodies by the billions every second without leaving any trace of their passage. Gravitational waves stretch and compress the space we occupy. Yet the distortion is so slight that without instruments of almost magical sensitivity, we would never know. Cosmic rays rain down upon the atmosphere, carrying news from distant galaxies. But their interactions with the air above disperse their energy across wide areas and long before reaching the ground, where we might feel their impact. The universe speaks in languages our bodies cannot perceive, and this is neither tragedy nor triumph, but simply the nature of things. We are made of atoms that interact through certain forces and at certain scales, and there is no particular reason why the cosmos should have arranged itself for our convenient observation. That we have managed, through patience and ingenuity and the accumulation of knowledge over generations, to build instruments capable of translating even small fragments of these cosmic messages into forms we can comprehend, represents a quiet achievement, a gentle extension of our awareness into regions of reality that evolution never prepared us to encounter. And still, the overwhelming majority of the universe's activity continues without our notice. Signals passing through us and beyond, carrying their information into the endless dark, speaking always in that silence between the stars that is not really silence at all, but only seems so to beings such as ourselves. When you look up at the night sky, you are seeing only a very small fraction of what is actually there. And this is not merely because the human eye is limited in its sensitivity, nor because the atmosphere scatters and absorbs certain wavelengths of light, but rather because the overwhelming majority of the universe is made of something that produces no light at all, something that emits no radio waves, no infrared radiation, no X-rays, no gamma rays. Nothing that any instrument we have ever built can directly detect, and this silent majority of existence makes up roughly 95% of everything there is. The stars you see, the planets that wander among them, the galaxies captured in long exposure photographs, the nebulae glowing with the light of newborn suns, all of this visible matter that we have spent centuries cataloguing and measuring and photographing, all of it represents only about 5% of the universe's total contents, and the remaining 95% exists in two mysterious forms that we call dark matter and dark energy, names that reflect not any actual darkness, but simply our profound ignorance about what these things truly are, and both of them are utterly, completely, perfectly silent to every form of electromagnetic detection we possess. The story of how we came to understand that most of the universe is invisible begins in the early 1930s, in the work of a Swiss astronomer named Fritz Zwicky, who was known among his colleagues for both his brilliance and his somewhat difficult personality. Though what concerns us here is only his scientific observations, which were conducted at the California Institute of Technology and the Mount Wilson Observatory, and which would eventually reshape our understanding of cosmic structure in ways that took decades to fully appreciate. In 1933, Zwicky was studying a collection of galaxies known as the Coma Cluster, which is located approximately 320 million light-years from Earth in the direction of the constellation Coma Berenices, and which contains over 1,000 individual galaxies bound together by their mutual gravitational attraction, all orbiting around a common center in a great, slow cosmic dance that has continued for billions of years. What Zwicky did was something quite straightforward in principle, though painstaking in practice, which was to measure how fast the individual galaxies in this cluster were moving relative to one another, using the slight shifts in their spectral lines caused by the Doppler effect. and then to calculate how much mass the cluster would need to contain in order to keep these rapidly moving galaxies gravitationally bound together rather than flying apart into the void. The results of this calculation were deeply puzzling, because when Zwicky compared the mass required to hold the cluster together with the mass he could account for by adding up all the visible matter, all the stars and gas and dust that he could see through his telescope, he found that the numbers did not match at all. And in fact, the cluster seemed to contain approximately 400 times more mass than the visible matter could account for. Zwicky called this missing mass Dunkelmaterie, which is German for dark matter, and while he proposed several possible explanations for the discrepancy, including the possibility that the cluster might contain vast amounts of cold, dim, non-luminous matter that simply could not be seen, his findings were largely ignored or dismissed by the astronomical community for several decades, perhaps because the implications were so strange and unsettling that most scientists preferred to assume there must be some error in his measurements or his calculations. The next major chapter in this story takes place in the 1970s. At the Carnegie Institution's Department of Terrestrial Magnetism in Washington, D.C., where an astronomer named Vera Rubin was working with her colleague Kent Ford to study the rotation of spiral galaxies, using a new and highly sensitive spectrograph that Ford had designed and built, which allowed them to measure the velocities of stars and gas clouds at different distances from the galactic center with unprecedented precision. What Rubin and Ford expected to find, based on the distribution of visible matter in these galaxies, was that stars near the outer edges of the spiral arms would be moving more slowly than stars closer to the center, because most of the visible mass, most of the stars, is concentrated in the bright central bulge of a spiral galaxy. And just as the outer planets in our solar system orbit more slowly than the inner ones, because they are farther from the sun's gravitational pull, so too should the outer stars in a galaxy orbit more slowly than the inner ones. But this is not what Rubin and Ford observed. Not at all. And what they found instead was that the rotation curves of spiral galaxies remained essentially flat, meaning that stars at the outer edges of galaxies were moving just as fast, or nearly as fast, as stars much closer to the center, which was physically impossible unless there was far more mass in the outer regions of these galaxies than the visible matter could account for. Vera Rubin studied galaxy after galaxy, accumulating data on the rotation curves of dozens of spiral systems. And in every case, she found the same anomaly, the same flat rotation curve that defied the predictions based on visible mass alone. And gradually, reluctantly, the astronomical community began to accept that Zwicky had been right all along, that galaxies and galaxy clusters must contain enormous amounts of matter that we simply cannot see. The dark matter that Rubin's observations required does not emit light, does not absorb light, does not scatter light in any detectable way, and interacts with ordinary matter only through the force of gravity, which is the weakest of the four fundamental forces and therefore the most difficult to detect at small scales, but which becomes the dominant force at cosmic scales where electromagnetic forces tend to cancel out. For many years, astronomers hoped that dark matter might turn out to be ordinary matter in some hard-to-detect form, perhaps vast numbers of dim brown dwarf stars, or black holes, or cold clouds of gas, or even rogue planets drifting through interstellar space. And these hypothetical objects were given the collective name MACHOs, which stands for Massive Astrophysical Compact Halo Objects. But extensive searches for such objects found far too few of them to account for the missing mass. And today, most cosmologists believe that dark matter is composed of some entirely new type of particle that has not yet been detected in any laboratory on Earth. The second great silent component of the universe, dark energy, was discovered much more recently, in the late 1990s, through observations of a particular type of stellar explosion known as a Type Ia supernova, which occurs when a white dwarf star in a binary system accumulates enough material from its companion star to exceed a critical mass and undergo a thermonuclear detonation, producing a flash of light that can briefly outshine an entire galaxy. What makes Type Ia supernovae useful for cosmology is that they all explode at approximately the same critical mass and therefore all produce approximately the same peak luminosity, which means they can be used as what astronomers call standard candles, objects of known intrinsic brightness that allow us to calculate distances by measuring how dim they appear from Earth, since a more distant supernova will appear fainter than a nearby one by a precisely predictable amount. In the 1990s, two competing research teams set out to use Type Ia supernovae to measure how the expansion of the universe has changed over time. Because it was generally expected that the mutual gravitational attraction of all the matter in the universe would gradually slow down the expansion that began with the Big Bang. And by measuring the distances and velocities of supernovae at different cosmic epochs, these teams hoped to determine the rate at which this slowing was occurring. One of these teams was the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory in California, and the other was the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins University. And though these teams were in direct competition with one another, employing somewhat different methods and observing somewhat different sets of supernovae, they arrived at the same startling and completely unexpected conclusion. The distant supernovae they observed were fainter than they should have been, which meant they were farther away than expected, which meant the universe had expanded more than predicted during the time their light had been traveling toward us, which meant that the expansion of the universe was not slowing down at all, but was in fact accelerating, speeding up rather than decelerating, as though some mysterious repulsive force were pushing everything apart with ever-increasing vigor. This was genuinely astonishing, because in a universe containing only matter and radiation, the expansion should inevitably slow down over time due to the attractive force of gravity. And yet, the observations clearly showed the opposite, that the expansion rate was increasing. And the only way to explain this within the framework of general relativity was to invoke some form of energy that permeates all of space and has a negative pressure, pushing space itself to expand faster and faster. This mysterious force was named dark energy, though, like dark matter, it is not dark in any ordinary sense of the word, but simply invisible and undetectable by any means other than its gravitational effects. And current estimates suggest that dark energy accounts for approximately 68% of the total energy content of the universe, while dark matter accounts for approximately 27%, leaving only 5% for all the ordinary matter that makes up stars and planets and people and everything we can see and touch. The discovery of the accelerating expansion of the universe was so significant that Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics in 2011. Though, more than a decade later, we still do not understand what dark energy actually is. Whether it is a constant property of space itself, as Einstein's cosmological constant would suggest, or whether it is some dynamic field that changes over time, or whether it indicates that our understanding of gravity is incomplete at cosmic scales. One of the most compelling pieces of evidence for dark matter came in 2006 from observations of a remarkable system known as the Bullet Cluster, which consists of two galaxy clusters that collided with each other at tremendous speed, approximately 150 million years ago, passing through one another in a cosmic collision that separated the different components of the clusters in a way that allowed astronomers to map where the mass was actually located. When galaxy clusters collide, the individual galaxies pass by one another like birds in two passing flocks. Their separation so vast that direct collisions between galaxies are rare. But the hot gas that permeates the space between galaxies in each cluster does collide, heating up and slowing down and becoming visible in X-ray telescopes as a bright emission region. And in the Bullet Cluster, this hot gas can be clearly seen lagging behind the galaxies that have already passed through. What astronomers found when they mapped the gravitational field of the Bullet Cluster using gravitational lensing, the bending of light from background galaxies by the foreground mass, was that the strongest gravitational pull came not from the visible gas, which contains most of the ordinary matter in the cluster, but from regions offset from the gas, aligned instead with the galaxies, suggesting that the majority of the mass had passed through the collision without interacting with anything, exactly as one would expect if that mass were made of particles that interact only through gravity. This observation has been called the smoking gun evidence for dark matter, because it is very difficult to explain without invoking some form of matter that does not interact electromagnetically. And while alternative theories of gravity have been proposed to explain galaxy rotation curves and other anomalies, most of these alternatives struggle to account for the Bullet Cluster observations, which seem to require the presence of actual matter, just matter of a type we have never directly detected. And so we find ourselves in the curious position of knowing that we inhabit a universe that is almost entirely silent, a cosmos filled with things that make no sound because they produce no electromagnetic radiation of any kind, no light, no heat, no radio signals, nothing that any of our senses or instruments can directly perceive. And we know these things exist only because we can feel their gravitational pull, the gentlest and quietest of all the forces, tugging on the visible matter that we can see and measure. The stars that seem so numerous on a clear night are like fireflies in an enormous dark forest, brief flickers of light in a vast and silent darkness that extends in all directions and contains far more than we will perhaps ever be able to directly observe. And this is neither frightening nor lonely, but simply the way things are. A fact about the universe that we have learnt through careful measurement and patient observation, and that we accept with the same equanimity with which we accept that the Earth orbits the Sun, or that water freezes at 0 degrees Celsius. The silence of dark matter and dark energy is not the silence of absence, but the silence of presence, the quiet of things that are there but that speak no language we can hear. And in this sense, the universe is rather like a library filled with books written in an alphabet we have not yet learnt to read, or a concert hall where the orchestra is playing at frequencies our ears cannot detect. And while we sit in what seems to be silence, we know now that the music is there, filling all of space. If only we could find the right instrument to hear it. And so we come now to the gentle work of gathering together what we have learnt, of laying out beside one another the quiet explanations for why the universe, for all its vastness and all its ancient fires, speaks to us in such a soft and measured way. Why the cacophony that might have been has, instead, resolved itself into something so subdued that we must build enormous instruments simply to catch its faintest whispers. The first and perhaps most fundamental reason for this quietude lies in the simple fact that our universe has not existed forever, that it carries within it a kind of cosmic clock that began ticking some 13.8 billion years ago, give or take a few tens of millions of years in either direction, which is itself a margin of uncertainty that would encompass several complete cycles of our Sun moving around the center of the Milky Way galaxy, and yet which represents a remarkably precise measurement when one considers the difficulty of peering backward through such immense gulfs of time. This finite age means that light, which travels at the fastest speed permitted by the geometry of space-time, has only had a limited amount of time to reach us from distant sources, and therefore there exists a kind of boundary, a horizon beyond which we simply cannot see, not because there is nothing there, but because the light from whatever might exist in those far regions has not yet had sufficient time to complete its journey to our small corner of existence. This horizon defines what we call the observable universe, a sphere centered upon our particular location, extending outward for approximately 46 billion light-years in every direction. A figure that might seem puzzling at first, given that the universe is only 13.8 billion years old, until one remembers that space itself has been expanding during all the time that light has been traveling toward us, stretching the distances and carrying distant objects ever farther away, even as their ancient light continues its patient journey in our direction. Everything beyond this horizon exists in a kind of permanent unknowability, at least for the present moment, though in principle one might imagine that as more time passes, light from ever more distant regions might eventually reach us, extending our view deeper and deeper into the cosmos. But here is where the universe has arranged matters in a particularly gentle and melancholy way. For the expansion of space is not proceeding at a constant rate, and it has not been slowing down as one might expect from the mutual gravitational attraction of all the matter scattered throughout the cosmos. Instead, driven by the mysterious influence of what we have come to call dark energy, the expansion has been accelerating for roughly the last 5 billion years. And this acceleration creates a second horizon, more final and more absolute than the simple light travel time horizon we have just described. When space expands at an accelerating rate, there comes a point at which the expansion carries distant galaxies away from us faster than light itself can traverse the growing distance between us. And this creates what physicists call an event horizon, borrowing terminology from the study of black holes, a boundary beyond which events can never be witnessed, signals can never be received, and influence can never be felt. Galaxies that cross this boundary are not destroyed or removed from existence. They simply become forever inaccessible to us, receding into a kind of observational oblivion from which no message, no light, no gravitational wave, no signal of any kind can ever return. The light they emit after crossing this threshold will spend eternity traveling toward us and never arriving, like a swimmer making strong and steady strokes against a current that flows faster than any swimmer could ever hope to match. The calculations that cosmologists have performed, using our best measurements of the expansion rate and the density of dark energy, suggest that this process has already claimed a remarkable fraction of the galaxies that nominally exist within what we might call the observable universe. The figures are quietly staggering, suggesting that approximately 94% of the galaxies whose light has reached us at some point in cosmic history are now receding from us at speeds exceeding the speed of light, carried away by the expansion of the intervening space, and are therefore already beyond our event horizon, already lost to us forever. The light we see from them now is old light, fossil light, light that departed billions of years ago when they were still within reach, and we are seeing them as they were, not as they are, and we will never see them as they will be, for they have passed beyond the boundary and will spend the rest of time moving farther and farther away into a silence that admits no possibility of reconnection. This process will continue, gently and inexorably, for as long as dark energy maintains its current character, and every galaxy beyond our local gravitational neighborhood, beyond the modest collection of perhaps 50 or 60 galaxies that are bound to the Milky Way by mutual gravitational attraction, will eventually cross the event horizon and disappear from our observable universe. The sky will gradually empty, or rather, the sky beyond our local group will gradually empty, as one by one the distant galaxies fade from view, their light stretched thinner and thinner by the expanding space until it becomes too faint and too redshifted to detect, and eventually until it stops arriving altogether as its source passes forever beyond the cosmic horizon. And what of the cosmic microwave background? That ancient whisper of creation that fills all of space with its faint thermal glow. The remnant light from the time when the universe first became transparent, when atoms formed and light was free to travel. This too is not permanent. This too is subject to the gentle stretching of the expanding cosmos. And calculations suggest that in approximately 100 billion years, give or take a few billion years, which represents a reasonable margin given the uncertainties involved, the wavelength of this primordial light will be stretched to dimensions larger than the observable universe itself, which is to say that the waves will become so extended, their crests and troughs so far apart, that no complete wave will fit within the horizon of observable space, and the cosmic microwave background will become literally undetectable, not merely faint, but genuinely absent from any measurement that could conceivably be performed. When that time comes, the evidence of the Big Bang, at least in the form of this particular relic radiation, will have been erased from the observable universe, smoothed away by the patient stretching of space, and any civilization that might arise in that distant epoch Looking out at a sky containing only the fused remnant of what was once our local group of galaxies would find no obvious evidence that the universe had ever been any different. No record of the vast cosmic web of hundreds of billions of galaxies that we can see today. No indication that space had once been filled with the thermal glow of primordial fire. No easy way to deduce that the cosmos had a beginning at all. The physicist Freeman Dyson contemplated these long timescales in a paper published in 1979, bearing the quietly evocative title Time Without End, in which he explored what kinds of existence might be possible in a universe that was slowly running down, slowly cooling, slowly approaching a state of maximum entropy. Dyson was not writing a work of despair, but rather an exercise in careful speculation, asking whether thought and computation, and perhaps something we might recognize as life, could persist indefinitely in an ever colder cosmos. And his conclusions were cautiously optimistic, suggesting that by thinking ever more slowly, by spacing out moments of consciousness across ever longer intervals, a kind of indefinite subjective existence might be maintained even as the objective universe grew dark and cold. But regardless of whether such long-term survival proves possible, the direction of travel is clear, and the universe is proceeding, with immense patience, but also with immense inevitability, toward a state that physicists call heat death, the condition of maximum entropy in which energy is distributed as evenly as possible, in which no temperature gradients exist to drive any kind of process, in which no concentrated sources of energy remain to power any kind of activity, and in which, therefore, nothing happens, not because anything is preventing events from occurring, but because there is no longer any thermodynamic impetus for change. In such a state, there would be no signals because there would be no gradients to produce them, no transmitters powered by differential energy flows, no organized structures capable of impressing order upon chaos. The universe would not be noisy or quiet in the ordinary sense. It would simply be uniform, featureless, the same everywhere and everywhen, a kind of eternal stillness that is not peaceful in the way we might imagine peace, but simply absent of all the conditions necessary for any kind of occurrence. The silence of heat death is not the silence of a library or a meditation hall or a forest at dawn. It is the silence of pure equilibrium, the silence of a perfectly still pond in which no ripples can form, because there is nothing to disturb the surface and no difference in energy to propagate once a disturbance began. Some theoretical physicists have proposed, though always with appropriate uncertainty and philosophical caution, that our observable universe might be only one among many, a single bubble in an effervescent foam of separate cosmic domains, each with its own physical laws, its own constants, its own history and future. These multiverse theories arise from various sources, from the mathematics of eternal inflation, from the landscape of possible vacuum states suggested by string theory, from anthropic considerations about why our particular universe seems so amenable to complexity and life. If such theories are correct, then the silence between these separate universes would be even more profound than the silence imposed by our cosmic event horizon. For these other domains would not merely be too far away to reach, they would exist in a completely disconnected region of whatever larger structure contains them all. as inaccessible as a number is to a sound or a color to a melody. Each bubble universe, if such things exist, would be forever alone, forever silent to all the others, surrounded not by empty space, but by something worse than emptiness, by the simple absence of any connection, any shared space-time, any medium through which signal might travel. An infinite number of cosmic civilizations might flourish and fade in these hypothetical parallel domains, each conducting their own searches for extraterrestrial intelligence, each listening for signals that could never come from beyond their own cosmic horizon, each eventually concluding, perhaps, that they were alone, and all of them correct in that conclusion, and all of them wrong, simultaneously isolated and accompanied by countless neighbors they could never meet. This brings us back, after our long and wandering journey through the physics of cosmic silence, to a kind of gentle acceptance of our situation. The universe is not maliciously quiet. It is not hiding its voices from us out of cosmic shyness or divine policy. It is simply that the conditions required for the transmission of signals across billions of light years, and the conditions that happen to prevail in our actual cosmos, are not well matched. And this mismatch arises not from any particular fine-tuning, but from the ordinary physical processes of expansion and cooling and redshift that govern the evolution of space-time itself. We cannot hear most of the universe because most of the universe has been carried beyond our horizon by the expansion of space. We cannot hear the earliest epochs because the light from those times has been stretched into invisibility. We cannot hear across the deepest gulfs of time and space because the inverse square law has diluted those signals below any threshold of detectability. And we cannot hear whatever might exist beyond our observable bubble because there is no beyond. In the spatial sense, only a boundary past which communication is forever impossible. And so the universe is quiet, not empty, but quiet, not hostile, but simply vast beyond our capacity to fill with sound. The silence that surrounds us is the silence of distance and duration, the silence of physics operating as physics must, the silence of a cosmos that is old enough to have cooled and large enough to have stretched and young enough that only a finite amount of light has had time to reach us. It is a silence that contains within it all the whispers we can still detect, the cosmic microwave background, the light of distant quasars, the gravitational waves from merging black holes. And it is a silence against which these whispers become all the more precious for their rarity. And so we return now to the present moment, to wherever you happen to be lying or resting as you listen to these words. And perhaps you might imagine yourself beneath an open sky on a clear and moonless night. The kind of night where the stars seem unusually numerous and the darkness between them unusually deep. And in this imagined or remembered stillness, you can let your breathing slow and your thoughts settle like sediment drifting gently to the bottom of a quiet pond. Because what we have been discussing throughout this narration, all these questions about light and distance and the peculiar silence of the cosmos, they all find their resolution in something as simple and immediate as the darkness you might observe on such a night. The ordinary and unremarkable darkness that exists between the stars and that has puzzled astronomers and philosophers for centuries until we finally understood what it was telling us. The darkness itself, you see, is the answer to the question we began with. The question of why the night sky is not blazing with the accumulated light of infinite stars in an infinite universe, and the answer written in that darkness is really quite profound when you consider it gently and without urgency. Because the darkness tells us that the universe had a beginning, that it has not existed forever, that there was a moment some 13.8 billion years ago when space and time and matter and energy emerged from conditions we do not fully understand, and everything that exists, every galaxy and star and planet and living creature, has unfolded from that beginning in the time since, which is an enormously long time by human standards, but not long enough for light from everywhere to have reached us. And so the darkness tells us about origins and beginnings and the finite nature of cosmic history. The darkness also tells us that the universe is expanding, that the space between distant galaxies is growing larger as time passes, and this expansion carries the most remote objects away from us faster than their light can travel toward us. Which means there are horizons in the universe that we cannot cross, boundaries beyond which we cannot see, no matter how powerful our telescopes become or how patiently we wait. And these horizons exist not because something is blocking our view, but because the fabric of space itself is stretching and carrying everything beyond a certain distance away from us faster than light can bridge the gap. And so the darkness speaks to us of motion and expansion and the dynamic nature of the cosmos. And perhaps there is something restful in knowing that even the universe is in motion, that even the grandest structures are participating in this slow and stately expansion that has continued since the beginning of time. And the darkness tells us too that there are horizons we cannot cross, limits to what we can know and see and touch. And while this might seem melancholy if you dwell upon it in a certain frame of mind, it can also be understood as a kind of natural boundary, like the horizon you might see from a ship at sea, which does not mean there is nothing beyond it, but simply marks the limit of what can be perceived from where you currently stand. And there is perhaps something peaceful in accepting that the universe contains more than we can ever observe, that the cosmos extends beyond our observable bubble into regions we can only speculate about, and that the darkness of the night sky is in part a reflection of these horizons, these gentle limits woven into the structure of space and time. In recent decades, astronomers have conducted surveys of the cosmos that reveal its large-scale structure in remarkable detail. And one of the most significant of these efforts has been the Sloan Digital Sky Survey, which began systematic observations in the year 2000 and has catalogued millions of galaxies and quasars and other celestial objects, mapping their positions in 3 dimensions to create a picture of how matter is distributed throughout the observable universe. And what these surveys reveal is something called the cosmic web, a vast network of structures in which galaxies are not scattered randomly through space, but are instead arranged along enormous filaments that stretch across hundreds of millions of light years, connecting denser regions where galaxy clusters reside. And between these filaments lie immense voids, regions of space that contain very few galaxies and that can span distances almost beyond comprehension. One of the most striking examples of these cosmic voids is a region known as the Boötes void, which was discovered in 1981 by astronomers Robert Kirshner, Augustus Ommler, Paul Schechter, and Stephen Schechtman during a redshift survey of galaxies in the direction of the constellation Boötes. And this void spans approximately 330 million light-years in diameter, making it one of the largest known structures in the observable universe. And within this vast spherical region, there are remarkably few galaxies, perhaps 60 or so, scattered through a volume that might be expected to contain thousands, based on the average density of galaxies elsewhere. And when you contemplate such a void, you are contemplating a region of space so immense and so empty that light traveling across it at 300,000 kilometers per second would require over 300 million years to make the journey. And throughout that unimaginably long transit, the light would encounter almost nothing, just the sparse and lonely galaxies that drift through that enormous emptiness like motes of dust in a cathedral. The cosmic web, with its filaments and voids, represents the large-scale architecture of the universe, shaped over billions of years by the gravitational attraction of matter and the mysterious influence of dark matter. And when you look up at the night sky, you are looking out into this web, though of course you cannot perceive its structure with your unaided eyes. You can only see the nearby stars of our own galaxy and perhaps a few smudges of light that are other galaxies. But the surveys and telescopes have revealed that behind that apparent simplicity lies this intricate cosmic tapestry. And the darkness between the stars is not just local darkness, but extends outward through these vast voids and along these immense filaments until it reaches the cosmic microwave background and the limits of the observable universe. And in this way, the darkness connects you to structures spanning billions of light years, which is perhaps a calming thought as you rest and breathe and let your mind drift. Let us turn our attention now to those who have experienced the silence and darkness of space more directly than most of us ever will. The astronauts who have traveled beyond the thin atmosphere of our planet and looked back at the Earth from orbit. And in particular, we might consider those astronauts who have conducted spacewalks outside the International Space Station, floating in their suits above the planet as it turns beneath them. And these astronauts experience something quite remarkable in terms of light and darkness, because the space station orbits the Earth approximately once every 90 minutes, which means that during each orbit the sun rises and sets, and over the course of a single day, the astronauts witness approximately 16 sunrises and 16 sunsets and 16 sunsets. A rapid cycling between brilliant sunlight and the darkness of orbital night that has no equivalent in our experience on the surface of the planet. And yet, despite this abundance of sunrises and the visual drama of seeing the Terminator line sweep across continents and oceans, what many astronauts report most strongly from their spacewalks is the profound silence they experience. A silence more complete than almost anything encountered on Earth. Because sound requires a medium to travel through. It requires molecules of air or water or solid matter to carry its vibrations from one place to another. And in the vacuum of space, there are essentially no molecules to serve this purpose. And so, when an astronaut floats outside the station, they exist in a realm of almost perfect acoustic isolation, hearing only the sounds of their own breathing and the mechanical noises transmitted through their suit. And beyond the thin shell of their helmet, there is nothing, no sound at all. Just the brilliant silent sun and the brilliant silent Earth and the brilliant silent stars scattered across the blackness. And many astronauts describe this silence as one of the most striking and memorable aspects of spaceflight. A silence that seems almost tangible in its completeness. This silence of space connects in an interesting way to our broader discussion of the silence of the cosmos. Because, just as the vacuum prevents sound from traveling between an astronaut and the objects they can see, the vast distances and expanding space of the universe create a kind of cosmic silence that prevents us from directly perceiving the energetic processes occurring throughout the cosmos. And in both cases, the silence is not a matter of nothing happening, but rather a matter of separation. A gap that information cannot easily cross. And this gap can be understood as protective in a sense, a natural insulation that allows us to exist peacefully in our small corner of the universe without being overwhelmed by the cacophony that would result if every distant explosion and stellar collapse and gamma-ray burst could reach us at full intensity. And so the silence is a kind of shelter, a veil drawn across the cosmos by the nature of space and time themselves. Perhaps the most famous reflection on our place in this vast and silent cosmos came from the astronomer Carl Sagan, who in 1990 wrote a series of thoughts inspired by a photograph taken by the Voyager 1 spacecraft as it was departing the inner solar system. And in this photograph, the Earth appears as a tiny pale blue point of light, less than a single pixel in size, suspended in a ray of sunlight against the blackness of space. And Sagan observed that this tiny dot was everything, that upon it every human being who had ever lived had conducted their existence. Every act of love and cruelty and creativity and destruction. Every king and peasant and saint and sinner. All of it taking place on this mote of dust suspended in a sunbeam. And his reflection was not meant to diminish humanity, but rather to place us in proper context, to help us understand both our smallness in the cosmic scheme and the preciousness of our situation. This tiny habitable world drifting through the immensity of space. That same Voyager 1 spacecraft continues to this day its journey outward into the cosmos. And as of recent measurements, it has traveled more than 15 billion miles from the Sun, making it the most distant human-made object in existence. Having crossed the boundary of the heliosphere, where the solar wind gives way to the interstellar medium, and from that incredible distance, Voyager continues to send signals back to Earth, transmitting data about the conditions it encounters in interstellar space. Though the power available to its transmitter has diminished over the decades as its plutonium power source slowly decays, and the signals it sends are remarkably faint, requiring the largest radio dishes on Earth to detect them, and the data rate at which it can communicate has dropped to approximately 160 bits per second, which is extraordinarily slow by modern standards, far slower than even the earliest dial-up internet connections. And yet, we can still hear this tiny whisper crossing the void, this faint signal traveling for over 22 hours to reach us from the edge of the solar system. And there is something profoundly moving about this, that across 15 billion miles of silent space, we can still maintain contact with a spacecraft launched in 1977, still receive its messages, and know that it continues its journey. The silence of the universe, then, is not an emptiness in the sense of nothing being present, but rather a veil drawn across the cosmos by the combined effects of distance and time and the expansion of space itself. And this veil softens and redshifts and attenuates the signals that might otherwise reach us from the far corners of the observable universe. transforming the brilliant violence of cosmic events into something gentle and ancient and easily overlooked. Like the cosmic microwave background that permeates all of space but requires specialized instruments to detect, and within this silence, we exist as observers, small and brief by cosmic standards, but possessed of the remarkable ability to understand something of what lies beyond our immediate surroundings. To trace the filaments of the cosmic web with our telescopes, and to hear the whispered signals from our distant spacecraft, and to read the story of cosmic history in the ancient light that reaches us from billions of years in the past. And so, as you lie here and listen to these words, and perhaps feel yourself growing drowsy and peaceful, you might reflect gently on the fact that you are participating in this cosmic observation simply by existing, that the atoms in your body were forged in the hearts of ancient stars and scattered by supernova explosions and gathered together over billions of years into the form you currently inhabit, and that the darkness you see when you close your eyes is in some sense connected to the darkness between the stars, to the vast voids of the cosmic web, to the silence that pervades the universe. And this connection does not diminish you, but rather situates you within the largest context imaginable. A small but aware point of consciousness drifting peacefully among the ancient light of the cosmos. Listening to the silence that is not empty, but full of meaning for those who understand what it tells us about beginnings and expansion and the gentle horizons of the observable universe. And in this understanding, there is perhaps a kind of peace, a settling into the quiet, a recognition that the darkness and silence are not things to fear, but simply the natural conditions of a universe that had a beginning and continues to unfold, carrying all of us along with it as we drift through the great quiet toward whatever comes next, breathing slowly, resting easily, at peace within the ancient and expanding silence of the cosmos.